Okay. Hello, everyone. My name is Michael. I'm going to be telling you about my fourth-year thesis project. So the title is Group Equivariant Neural Networks, and basically what that is it's how you get a neural network to intuit physical symmetries. So a lot of the problems in machine learning at the minute is the lack of generalizability of the models. The reason why that is because they don't know how to extrapolate in a physically reasonable manner from the training set. So that's basically what this takes aim at. We can show them a very narrow perspective on the training data, and it should be able to reasonably extrapolate to other configurations, I guess, connected by some symmetry. And the symmetry we'll address in this case is the Euclidean symmetries in 3 dimensions. So that's translation and rotation. So basically, I should be able to show an example, a particular atomic configuration, because this project is in condensed matter, and I should be able to extrapolate to every other copy of that configuration, but I guess differing by either a translation or a change in orientation. Anyways, I'll go through it in turn. So a very quick tour de force of machine learning. Basically, your training data consists of pairs of input data and output data. You try to build a model that will get you from inputs to outputs. It's pretty straightforward. The, I guess, components of your model are the weights. So this is, I guess, how it combines all of the different aspects of the input to give you your output. The, I guess, preliminary neural network is this really densely connected one here. This is called an artificial neural network or a multi-layer perceptron. The details of it isn't all that important. What this doesn't show is, okay, so I should say, basically what connects one layer to the next is effectively a weighting of the extent of excitement of a node. And what you essentially have is a matrix of weights connecting layer to layer. I'm not going to get too into the weeds on this because it's actually not too important. One of the things that picture omits is an activation function. So an activation function is like, it's what lets you introduce your nonlinearity into the model. So where I was saying that the layers are connected by matrices, if you only use matrices, then you can only hope to capture linear functions. So you have to introduce nonlinear functions in order to get your model to, I guess, get that expressivity. You should expect that it be able to, capture nonlinear behavior, because nonlinear behavior is all over the place in physical systems. So how this works is you initialize this function with random weights. You throw your input at it. You throw an input at it that you have a corresponding known output to. And you compare the output of your function to the known output. Generally, you have some error function that'll tell you exactly how badly it performed. But the error function on its own is not enough to bring you towards a decent model of your physical system. It tells you like by how much you're wrong, but it doesn't tell you the ways in which you're wrong. And the ways in which you're wrong are captured in the derivative of the error function. So the derivative of the error function, the gradient, you can see with this like weird surface here, the plane that this surface is like, I guess, yeah, the plane of this surface that we're using to project it is a space of weights. So when we take the gradient and we find the direction of greatest slope, we are finding which weights to assign blame to. And so we can see which ones are contributing the most to the error, however we've chosen to quantify the error. So then backpropagation is taking that derivative, finding the extent of the gradient in each of the directions, or the extent of the derivative in each of the directions, and just traveling a little along that slope. There's loads of different ways to do this, and I'm skipping over a ton of the details, but that's essentially machine learning. So how do we pair that with the general covariance of physics? basically what I'm saying here is physics shouldn't depend on your coordinate system. I think it was Weil that said it should be observerless, and general relativity to a pretty high degree of accuracy suggests that your laws of physics should not depend on where you are. But that comes in conflict with a principle of machine learning, which is the universal approximation theorem. So theoretically, you should, by some combination of layers and activation functions, be able to achieve basically be able to model any function. But we know that physics doesn't take the form of any function. It takes the form of these functions which are observerless. They're coordinate independent. So how do we restrict our model to these functions? You can see here, for example, right? Let's say, like here, all functions. Can you see the arrow? Yeah. So why might the let me see. Why might all learnable functions sit outside the equivariant functions, the ones that we know to be true? Well, that's generally because of the failure to extrapolate that I mentioned machine learning models have. So like, say for example, if you have a Lennard-Jones potential, so this is like, for example, the force that an electron might feel as it's getting closer to a nucleus or something, right? It vaguely looks like this. Yeah, have you seen this kind of thing before? You should expect that, or yeah, if it gets too close, you should expect a strong repulsive force. Well, if you happen to show the model data around here, if you plot the model in this radial direction, it will fit your data, but it could well just, I don't know, head off a cliff afterwards because it's no reason to adhere to any underlying physical principle. Now, it's not like integrating equivariance in can give you this kind of distribution, but it can stop it from being unreasonable when you translate your system. When you translate your system, it'll still remain physically reasonable. So that's what is referred to by the equivariant functions here. Those are the ones which are coordinate independent, and that's the area that we want to take aim at. Right, so oftentimes like a problem can help sharpen the question. So like, how will we integrate this kind of equivariance into our model? We'll take this toy example of a water molecule, and we'll bend the bond slightly. We might perform some symmetric or asymmetric stretching, and we'll observe the change in molecular energy that happens, right? This can be pretty easily simulated. One of the ways that we depart from conventional neural network stuff is, like, say, for example, image processing, where a lot of this was developed. That's developed on arrays of pixels. That doesn't really suit us. Coordinate positions don't, I guess, map very well to a discretized grid like that. Because you can see that even with this molecule of benzene here, right, the coordinate positions are really imprecise. So what we do instead is we use a graph neural network. So we can represent all of the atomic positions with Dirac delta functions. So we can, for anyone who doesn't know what that is, it's just a very, very precise function, or like I guess, localized infinity. It's just, we know exactly where the atoms are when we use a graph neural network as opposed to a grid neural network. But anyways, that's kind of getting away from the equivariance. Equivariance is basically, if I perform some transformation, the ones I'll be addressing are where this D of R is just some rotation matrix, right? So if I transform my input is X and my weights are W. If I transform my input, I should expect my output to transform predictably, right? So what does that look like? It's like if I have, for example, here's my water molecule, and I have a force, for some strange reason, located on this node or this atom in the molecule. If I then rotate this, so you can see, okay, right, it's perpendicular in this case, right? If I rotate it, so I perform this kind of rotation, I should expect that this force, which is a vector, should rotate in the exact same manner, right? Okay, so If I perform a rotation of my molecule, the vector associated with the force changes predictably. We don't usually restrict ourselves to just vectors. So there's different kinds of these geometric. To generalize this, we will look at a geometric tensor. So I'll explain what that is in a second. If we consider, for example, two vectors right on the left-hand side here, and we consider their tensor product. So I know there's some first years here, so I'll just explain really briefly what that is. So if I've got vector 1 and vector 2, the tensor product is just a 3 by 3 matrix that looks a bit like this. x1, y2, x1, y3, x2, y1, and so on. Okay? It's just basically every pair, and it's a 3 by 3 matrix. We can decompose the range of this tensor product, right? We can decompose this vector space into a direct sum of 3 distinct vector spaces. So the first of which is the trace, and the trace just corresponds to the dot product. We know that the dot product encodes information about length and angle. And if we take this water molecule and we perform any kind of rotation, we should expect that the dot product between the edge vectors is unchanged. So effectively, if we look here at the top equation, right, if I perform a rotation on my input x, my input vector is x, the output, the corresponding rotation of my output is just the identity matrix, right? If a particular operation is calculating a dot product, then a rotation of the inputs won't yield any change in the outputs. If instead it is, okay, let's check out the second vector space here. So this is the cross product. How should we expect that to change? Well, if I have 2 input vectors of my water molecule, cross product is, I don't know, just perpendicular to both of them. As I perform a rotation of my water molecule, the cross product will, the vector associated with the cross product will transform predictably. So in this case, it would be f of rotation of my input will give me straight up just a rotation of the output. This is nothing complicated. Where it can get a little bit more complicated is in higher order geometric tensors. So in the other vector space that this geometric tensor product ends up in is this 5-dimensional space of symmetric traceless matrices. You wouldn't have come across and you wouldn't have been familiar with it. But basically, the weird thing about this is unlike the dot product, which is invariant under rotation, and the cross product, which changes, I guess, predictably or accordingly with the rotation, these symmetric traceless geometric tensors will rotate twice for every 1 rotation of your inputs, right? So you can imagine, say for example, I have like a feature like this. Okay, let me see if I can. So if we look, this might be kind of weird to think about, but if I look at, like, say, let's say an object like this, and I rotate it in this plane, you can see that after a rotation by 180 degrees, the object will be left invariant. It will be left basically unchanged. That's what I mean by you only having to rotate, it rotating twice for every 1 rotation you perform, if that makes sense. Okay. Yeah, basically this is the collection of all of these higher order geometric tensors. So this guy, for example, up at the top left here, that's what we call like an L equals 0 term. So that's the invariant. That's like the dot products that I mentioned before. These guys here, these 3 guys, are the L equals 1. So these transform like your vectors. You know, if you rotate your input, these guys will rotate predictably. These guys, these guys here, these are L equals 2. So when I'm talking about like L equals 1, L equals 2, I'm talking to orders of spherical harmonics. And spherical harmonics are just, well, I mean, technically they are the basis of the Fourier series on the sphere, but that's really not important. You can basically think of it as how many times a feature would rotate if you were to rotate the inputs, right? So these guys here are, for example, this is one of them, right? This is one of those guys that if you rotate it once, the feature is effectively rotated kind of twice, if that makes sense. It's kind of weird, but anyways, so the way that this model works is you presume that your function can be split up into an angular part, a product of an angular part and a radial part. What we do is when we run our function through, or when we run our input through our function, we want the function to respect the angular part, as in to use the fact that we know how the angular parts must transform, that they must transform predictably, and we actually train the model only on the radial parts. This is the only complicated slide. Basically, the way that this is done, okay, the important thing to know here is, or to notice, is the V1, V2, and V3. So the reason why they're important, a lot of these networks just come down to bookkeeping. So like when I know my output vector spaces, I know how each one of them must transform. So that's all I really need to keep track of. Because once I know my input vector space and my output vector space, I can basically deduce the rotation that connects them. That's essentially it. So as let's say, okay, for example, right, this top left process here, all it's doing is like, for a given node in the network, it's like considering atomic information, as in, is it oxygen, is it hydrogen? Then it's loading it onto the edges. Then it's basically what these edges are is like, you're considering your atomic configuration in an angular sense. And it's the way that these steps combine with one another, say like step 3 here to step 4, is through these tensor products. Because we know that we can build equivariant, I guess, functions out of tensor products. An equivariant function, sorry, the tensor product is this, just as a reminder, and the equivariance is just the fact that I know how the individual spaces transform. So that's why we use tensor products. It's actually important to note that, see this guy up at the top right here, the traditional neural network, the connections, the matrices that join up all of the layers, there's no way you can get equivariance into these guys. You have to use something like a tensor product to link all of the bits of information in your network. So yeah, okay, now this is the slightly weird bit, and this is how the machine learning gets involved. This is how these tensor products happen in the network. Let me see, I'll describe a little bit of the notation. Can you see where the arrow is? Yeah, so let's say this left-hand side here. All this says is I've got 2 scalars and I've got 3 vectors. And here I've got, again, 5 scalars, and this is a pseudo vector. So a regular, I should say as well, one of the other symmetries that we're trying to get involved with this network is parity, an understanding of parity. So there's some vectors for which if I perform a parity transformation, like if I mirror this guy across here, I should expect this vector to change predictably, right? And this guy then is a pseudo vector. But then there's other guys that you shouldn't expect them at all to change under, and they're not as common and not really as physical or something that we would have be used to seeing. But there's some quantities. If this was, for example, a pseudo vector, when we perform a parity mapping, when we perform a mirroring, this guy is actually left unchanged. So that would be an even parity vector. It's not all too important. The cool thing, though, is we can combine this combination of geometric tensors, this combination of geometric tensors, using a naturally defined tensor product. And we get this whole host of outputs here. They combine in kind of predictable ways. Like if you have an odd geometric tensor and an odd geometric tensor, and you take their product, they'll give you an even and even will give you an even. The parity acts as you'd expect. If you take a scalar and you tensor product with another scalar, you can't expect to get something that resembles a vector, right? So they're not so difficult to understand. Where this network introduces the learnable characteristics is in the weighted tensor product. So what happens here, the way in which this guy is distinct from the natural one, is these outputs here are combined to give these outputs, and the connection between them is this kind of stuff. So long as I'm basing the whole lot off of tensor products, but I just happen to combine the outputs, I happen to just weight the outputs in the usual sense, I can actually still preserve equivariance. So I'd just slap a neural network between these two outputs, and that's the learnable part of the network. Okay, so this is, I'll explain a bit about what this slide is. This is kind of a slide capturing its performance. So at the top 3 lines here correspond to where I would only use L equals 0 terms. So this is a network that's built on the scalars, right? So it can't capture, it can't I guess, generate any angular features at all. It just carries invariance everywhere. And it can only do so well, right? And if we let the network use higher order spherical harmonics, so we let it consider features that have like, different frequencies and stuff like that, it performs considerably better. What's really interesting though is not only does it perform better in that it's lower down, but also you can notice as well its slope has changed. So not only is it performing better, but it's actually also learning faster, which is pretty cool. So yeah, basically that's kind of like the holy grail of machine learning, is like if you can make things learn a bit quicker. That's kind of how it works. I don't want to go into the details because it's an awful lot of code, but that's the main gist of it. I kind of want to tie it back to one of the outstanding problems in machine learning, which is interpretability. So when you build your network and it's based solely on these kinds of things here, these artificial neural networks, the multi-layer perceptrons, it can be very vague as to what they're doing. Whereas when you have something like this, where if you felt like it, and I wasn't arsed coding it, you can look at a given node and see how it's regarding its atomic neighbors in an angular sense. It does an awful lot for interpretability. And interpretability is quite important, right? Because it's puzzled people like Feynman. So Feynman was of 2 minds when it came to theoretical investigations. One of them was him being a strict operationalist. So in that case, you don't really care for what's going on behind the scenes, right? You just care that the maths works out. You don't have to worry about, say for example, in quantum mechanics, these debates between interpretation and stuff like that, Copenhagen, many worlds. He's like, fuck that shit. I don't care. John Gould is actually an awful lot like that as well. He does quantum information in 4th year. He's a very strict operationalist, and he just doesn't care, right? And that's all fine and well. But you get to see this other opposing facet of Feynman, which was the anti-operationalist. So he cared very much about knowing and understanding and intuition and holding two competing theories that were presently phenomenologically indistinguishable, but may offer some slightly different psychological facet that let you discover something new in one avenue. He gave this really nice example, and I think it's pretty apt here, of the Mayan astronomers. So these guys, they had, I guess, insane predictions of where planets would end up. Just basic astronomy. They were really, really good at it, but it was all just arithmetic. They had no idea. They had no idea why it worked at all. And so he gives the example of someone coming along and saying I've got a theory. Maybe it's maybe these guys are in orbit, and maybe there's a force, gravity, and blah blah blah. And we can't simply discard those people that come with those ideas, just because it might not be fully formulated yet, even though the arithmetic as we might presently have it is superior. Machine learning is kind of in this place at the minute, in that we've no idea how the fuck it works, but it really, really does. So there's people who are like very strict operationalists, and they believe, oh, just scale it, right? Don't bother interpreting it at all. It works, and the bigger you make it, the better it'll be. And it's basically like they're essentially advocating for like Mayan astronomy. You know, they really don't care for interpretability. I would err more on the Feynman side of things, that, you know, it's impossible not to acknowledge the power of these systems, but we cannot let them be completely uninterpretable. And the fact that when we introduce this interpretability, we get better learning, like accelerated learning is a really motivating and positive outcome of this project. So yeah, that's the technical side of things. I guess I better give it to Chantelle now, if you're up for it. Yeah. We'll chat about like the technicalities of like, you know, getting the project and the supervisor and all that stuff at the end, I guess. Yeah.
Newfound technologies. Hi guys, my name's Chantelle. I'll be talking about my final year project, which I did last year. So I'm now in a master's, so this is all behind me, and I have more experience to kind of talk a little bit more about maybe what you'd get out of it with the idea of hindsight and a bit of time after I've actually done it. So I'll be going through more of my journey. I won't be going too much into detail because, unlike our last speaker, it's not as, let's say, cool or as open to get really into the details. But okay, so the title was this TTbar deformation of non-relativistic models, which is a lot of gibberish to most people who do not know what the TTbar deformation is. So this is in the School of Maths, and my supervisor was Professor Sergei Frolov. So first of all, well, what is this? What are we actually dealing with? The idea is that this TTbar is some combination of elements of what we call the stress tensor. So this object basically encapsulates the conserved currents that relate to energy and momenta in any theory. So in any kind of good, reasonable theory, you're going to have this translation invariance and translation also in terms of time. So that's where you get these conserved currents. So it's pretty fundamental. If you have done classical field theory, here it is. But the idea is that if you have an undeformed action, you can actually couple that action to some sort of operator. So you just slap on at the end some parameter, some operator, and overall that will be a new theory. And in that case, it'll satisfy what we call a flow equation, which is kind of defines how the theory deforms and how it changes. And so when I talk about it's a different theory, that means that the equations of motion and the solutions, they're all different, but they're related by some parameter. And so in this case, you can see the bottom, that's the example of the flow equation, and that's what the actual TTbar operator looks like. So it's just the determinant. But the idea is that it's gained a lot of interest in the last few years, around maybe 2016, where people were finding kind of interesting properties of this operator, because obviously you can think about any old operator and you can slap it on and see how it looks like. But the idea is that this is quite special, but a lot of the properties, to really basically understand the importance of it, you need to go pretty deep into quantum field theory to really understand why people are liking this so much. But one of the things that I've said there is that it preserves what's called integrability, which I'll talk about a little later. But also, interesting thing is that if you have the spectrum of energies, right, in the undeformed theory, or even just your expression for the energy, that actually satisfies a differential equation with respect to the deformed energy spectrum. So in this case, basically, your spectrum in the deformed theory is fixed, which is cool, because a lot of the times, this is one thing that you'd want to actually find out from a theory. So now we actually, with this, you can imagine that instead of, let's say, some particular theories which we've managed to solve the spectrum in some sort of way, now we have a whole, well, ideally, we'd have a whole one parameter family of theories that we know the energy from. So the idea for this project was that my supervisor, about maybe a year or two before the project, had published a paper where he had found a new way of actually finding the deformed models. And it's a pretty nice way. It's actually quite an algebraic way, where it's very independent of your undeformed theory. And he wanted to develop this. And the idea was that, okay, I would learn about this TTbar deformation. I would bang my head against some quantum field theory to try and understand why everyone was kind of excited about this, but also to understand and go through exactly this method that he had, and then apply it to some models and just perform some investigations about it. So what do the solutions look like? So at this stage, it was kind of, when you have, it's a nice mix of having a pretty straightforward idea of your project and a nice open-ended where you have just investigation. And when you have the word investigation, that means that you can't really predict what you're going to do at the end. So for some people, that's really nice. So in terms of what I needed, let's say, for this, was actually for practical calculations, it was just classical field theory. There wasn't anything spectacularly difficult about actual calculations and even looking at the derivations, because it was not very, let's say, complicated. What was complicated was sometimes understanding where things came from and the theory behind things. But it wasn't too bad. And another thing which actually I found really helped, and this only I realized in hindsight, is actually the physics labs that you TPs are sometimes maybe forced against your will into. Because that's really the only place where you're forced to actually write academically. I always joke about other people, in different fields, and it's like, wow, we have to write essays. And you realize, we don't write. And that's an important thing. And we don't really read, or at least as much as other people where you'd have to research for essays. We don't do that regularly. And so just kind of basically putting your effort into those things will really help when you basically start to do this. And you will look like our Gothic friend. You will. And you will continue to look like him for a good while. So there is a lot of information, especially when you're going into something formal like this and something pretty niche. And even at fourth year level, you're still learning things. You're still only learning quantum field theory if you're masochistic enough to actually go ahead into that. So there's a strategy in approaching things that you don't know, things that you have no idea what's happening. You don't even know the words. So that's something that my supervisor helped, because it kind of guides you what you should do first. So in my case, okay, I did the calculations first. And then from that vantage point, I suppose, I can start to understand other things. Okay. So in my case, what did this starting point look like? Okay, so that first action wasn't the actual starting point. there was a simpler one, which is kind of got me used to the idea behind this. But the idea is, this is kind of what quite a general string action looks like. So this method was actually couched in string theory. Now, some people would say that it isn't real string theory, because it's a toy model where we actually don't look at the important, let's say, structure of strings where they actually oscillate and all of that stuff. It's basically just a tool to carry basically our calculations. But the idea is that you take this and you assume, okay, this is our undeformed theory, and the usual idea that you would, let's say, solve for the dynamics of this is basically you have two constraints called the Virasoro constraints, and you have an extra, let's say, redundancy in your system, so you have freedom to fix a gauge. So the usual procedure is you switch to these light cone coordinates, which is actually just if you have your, let's say, a time direction and some sort of spatial direction, you're just rotating it 45 degrees. That's the idea, and you fix a specific gauge, and everything's fine. You can actually then find even your Hamiltonian in terms of all the other fields, or in this case, variables, or both. But in this case, almost like magic, the method was that when you switch to these light cone coordinates, you change them slightly, and you add in this deformation parameter, so in our case, this alpha. And like I said, almost by magic, when you actually do the exact same computation, you will actually be able to find the Hamiltonian, and hence the Lagrangian of your theory. Now, there's a lot of subtleties here, and there's a lot of kind of imposing more constraints and, looking at, okay, I want certain behavior, and also fixing it so that when it goes, let's say, it behaves nicely when you take alpha going to 0. So a lot of those things. But the overall idea is you take this undeformed Lagrangian, you manipulate it into this form. So you see that every term here only has one derivative, either time or space. It's called a first-order form. But the idea is you identify these, and then you can immediately even write down, without calculation, what your deformed Lagrangian is. So that's a pretty, let's say, powerful statement, because there wasn't anything like this before. And so you can see that, it may look quite nice, but this V on the bottom is dependent on the fields. So you can imagine when you start to do your equations of motion, they get changed quite horribly. Oops, okay, went too far. So after I did that, then I can actually apply it to this nice model. So this nonlinear Schrodinger model, it kind of looks like the Schrodinger equation, except in that you'd have your potential being some sort of, let's say, potential depending on your coordinates. But in this case, it's actually depending non-linearly on the fields. And so this is quite a widespread model. It's very common in optics, where your, let's say, wave is propagating through some sort of medium which has a nonlinear response to the electric field. But it's also a pretty simple model, and it's integrable, which again, it's just later. But the idea is that, first of all, I have to look at this. I have to get used to, let's say, almost perform an assignment on it. I have to find its symmetries, its equations of motion, get used to the calculations. And then I manipulate it into that first order form. It includes, let's say, adding in more auxiliary fields. But at the end, I actually get a deformed Lagrangian. So this V0 is, I'm pretty sure in this notation, what this looks like. And it may look nice, but this lambda in the square root is not a nice expression. But we have it. And I had to check that it satisfies the flow equations. But there we go. That was the first stage kind of done. And after this, I had a lot of directions that I could take. So on one hand, I could look at how the Poisson structure of this deformed theory changed. So if you're not familiar, you can basically, you have these Poisson brackets, and it's basically an operation on your Hamiltonian that you get out your physics. But a lot of, let's say, proofs about even integrability, because this is actually classical. I failed to mention that, but this is all classical that I'm dealing with. It's, even though a lot of the properties are in the quantum, we can still look at the classical area. Okay, so I'm rambling right now a little bit, but okay, let's go ahead. So what did I choose? I would joke that I chose pain. So what I chose was the idea of integrability and finding a lax pair for the undeformed theory. And so what is this integrability? It's actually a very rich subject, both in classical sense, in terms of even historically, and in a very modern, like, forefront of research in, let's say, quantum fields, very important. But the idea is, if something is integrable, it loosely translates to being able to solve the theory exactly. So that statement would mean different things in different kind of regions, classical or quantum. But the idea is that if you can manipulate your equations of motion into this form. So this is called the zero curvature condition. So basically, these U and V, they are matrices, just 2 by 2 matrices. And this commutator is just a matrix commutator, no quantum, once again. But the idea is that if you have these U and V, okay, when you actually set this equal to 0, you will get back your equations of motion of the system. So it encapsulates the dynamics of it. But also, you can actually find all of your conserved charges and currents within this, at least this U, I think. Maybe it's V. I don't remember even now. But in one of them, you can. And so the idea is that in at least a field theory, this will give you an infinite tower of conserved charges, which is roughly equal to the infinite amount of degrees of freedom in a field theory. So its statement is a lot more precise when we're talking about things like coordinates and just mechanics rather than field theory. But the idea is, if I can find them, if I can find matrices that satisfy this relation and give me the equations of motion, great. Then that opens up a very rich area of powerful tools to be able to analyze the theory, not just looking at the Lagrangian. But unfortunately, there's no general procedure. There is no sort of like you do this and you get it out. No, it's kind of educated guesswork, luck, and pain. So unfortunately, I didn't find the exact solutions. It took me a long time. There was a lot of frustration. So I was able to find, let's say, the first order corrections, which is nice. But I suppose my approach devolved into brute force after a few attempts. And it's sort of like, I'd like to say it like a message that sometimes this will happen, and it's okay. And it's good to know when you devolve into something that you're not getting any results out of, you can leave it. So my supervisor saw that I wasn't getting anything for this. There was many Mathematica notebooks, so too much, basically. So we changed direction. So instead of looking at, let's say, the lax pairs, we would actually just go straight to solitons. So what is the soliton? No, let's say, definite definition, but it's a structure, it's a wave solution that's exclusive to nonlinear systems. They are waves, but as you can see in this animation, they don't obey the superposition principle. So when they scatter, they only shift by a phase, and the idea is they're very stable, and their amplitude doesn't change very much with their propagation. So in this case, you can actually find soliton solutions straight from lax pairs if you have them. However, I didn't, so I could still actually use some assumptions, some boundary conditions, and actually find soliton solutions for the nonlinear Schrodinger model. There we go. So this is what these babies look like. So it's not trivial because the equations are not fun, but they're doable. So one of the main techniques was basically learning how to use Mathematica and using it and not making mistakes. But okay, so I found them, and my next step was really to classify them. So classify the different regions. So you see there's like a bell kind of behavior, I suppose, with increasing the deformation parameter, and there's all double bell and kind of other weird stuff going on. So the idea was that my investigation, in this case, was really classifying and describing the entirety of this behavior. You know, what regions there are, what parameters, and how the parameters change this. So it was really interesting to see and basically to learn how my supervisor deals with presenting such, let's say, complicated results. So that was nice. But okay. So then I had a mini crisis. Not really, but around January, I was kind of writing these things up. And I suppose if this didn't happen, I would have, let's say, continued on maybe more of a theory. But the problem was that there was another group that was also working on the TTbar. I'm pretty sure they were Italian. So they had another way of finding deformed theories. And their way was through a coordinate transformation, which is actually really helpful in a lot of ways. So they published a paper about the nonlinear Schrodinger model with more solitons and exact lax pairs. And the problem was that my supervisor did want to publish a paper based on our calculations. So this meant that we had to do something more. So what we did was we chose another model. And I call this equation there the Korteweg de Vries model of Rise. But in reality, it's actually much more general. So the Korteweg de Vries might be some sort of specific values of this mu, g, and h. So my supervisor called this the Gardner model. But the idea was, OK, this is also some model. It's integrable. And with the other group, their, let's say, coordinate transformation approach was highly dependent on the underformed theory. So you had to solve a differential equation. And for something like this Korteweg de Vries model, when you transform it into, when you basically get the Lagrangian, you will get terms where you have like a fourth derivative in there. So you can imagine that it's, at least it seems nearly impossible to get the Lagrangian with their method. So that's what they did. That's what we did. So we did the same thing. We got the deformed Lagrangian. I'm not going to put it in because, number one, we had to introduce a lot of auxiliary fields, like 3. And I don't think it was possible, or at least at first glance, with some headbutting and massaging the equations, to actually solve it in terms of one variable, like I did with the nonlinear Schrodinger equation. So it just tells you how kind of little weird this equation is. But OK, so you can also see that it has also weird behavior, but still, once again, classification of these. And this is only also one direction of this, but this is what it looks like. And so, OK. And then that went much faster than the nonlinear Schrodinger equation. And you'll find that looking back, you might ask yourself, why did this take me so long? And it seems to just be a natural way in research that when you're learning, you're going to seem to do it a lot slower. But then the final step, when you're actually trying to write stuff, you realize that you really need to know it when you're writing it. And you really see at every sentence when you're trying to back up your statements. You see all of the, let's say, holes in your knowledge, all of the questions that you haven't answered. And so basically, in my case, in the final month or kind of month and a half, maybe 2, I had to basically go through everything that I learned at the very start and go through it again and write it down properly. And I think it's something very common with people. It's a common advice that people would give. But then this was where I really kind of collected a lot of stuff. So even went through calculations in string theory and calculations in, let's say, where this even TTbar operator came from way back in 2000. And it may not be specifically relevant to my calculations, but that's the idea, that it's still all about learning and gaining knowledge and kind of explaining some things, I suppose. And, okay, but in the end, so I've made some kind of, let's say, maybe disparaging remarks, some frustrations, but in the end, I was really overall happy. And things like this, I think, especially if you're doing something that's theoretical, the main idea is that you learn. You learn niche things that will help you, or you learn that maybe you don't like certain things, and that's okay. Or even you learn how to approach problems and how to project manage. So you shouldn't kind of be, let's say, worried about results or anything like that. And your report, I think, is not like a paper as well. So it's very much chronologically detailing your journey, just as I kind of did there, and putting in all the pitfalls and all the kind of workarounds and everything like that. So, and I really did enjoy having meetings with my supervisor, and I think it's a really nice thing to be able to break down that barrier of student-teacher that comes from secondary school, and really start talking to people more of a peer-to-peer level, and you can ask them about anything and get to know what is it actually like researching, what's the politics maybe, what certain things can happen. So it's very nice to even ask just normal things, I suppose. And you kind of, that's basically gives you a start, because a lot of research is also about networking. But I hope I haven't gone too much. Okay, all good, all good. But I hope you've enjoyed, and thank you very much once again for listening. Who do I give this?
Any questions about the process? Because Chantelle went for a maths project and I went for a physics one. My supervisor, Stefano Sanvito, I think one of the differences between myself and Chantelle's project is unfortunately Stefano has no knowledge in the area, even though he's a complete expert in machine learning and artificial intelligence. This is just, it was I guess an opportunity for Stefano to bring knowledge on group equivariance into his group. So like a low risk strat for bringing that in. So yeah, I mean, if you have any questions on either one of the projects now, as well to ask.
Is there a big difference between the final product, whether you do it in maths or physics?
I would say yes. I would say I don't know how much, let's say, purely theoretical things can happen in physics. I would say there's a lot of,
Yeah, no, not an awful lot.
Yeah. So in maths you can find projects where it's almost purely theoretical, almost purely sort of literature review. Now that will contain, going through calculations, understanding exactly what step and really kind of expanding your knowledge. But you won't be in a lab. You might not get pretty pictures even. So that's the kind of results. Your result might be knowledge, more so than results. Sure.
Is there a way to kind of tangibly relate when you mentioned the TTbar deformation? Can you correspond that to like a physical process?
I don't know. That's the thing. It's very far removed from actual physics. Now, who knows, I could have gone more into the physical nature. So let's say when I'm looking at these actual salt-on solutions, I could have gone into more experimental stuff and kind of looked at different properties of materials, where it could propagate into. So you could, if you were interested in that, even something like this, you don't have to keep going into the maths. That's what I'd say. And it was a slight question that arose, but really it's just keep calm and do the maths. And kind of, let's say, related more to the properties in a quantum sense than any strictly theoretical, physical processes, if that makes sense.
Do you have any tips for kind of like time management in terms of like not falling behind on the project, but also like staying afloat in your classes and working?
I'm not sure. Probably use Christmas to your advantage with the project and stuff. I would absolutely echo what Chantelle was saying about it. Wondering how in the name of God you took so long in doing some aspect of your research. Like I know with my own stuff, like code that would take me, I don't know, an hour to implement, took me a week and a half, 2 weeks to understand and do at the start of the project. So what I would say is start it early and start, I guess, meddling around with the intricacies of your project early on, because you're likely going to have to use them again in some capacity later in the project, and you may as well be quick at them by that point,
I would second that, and I suppose note-taking, when not only in classes, but actually like when you learn and when you read from books, is a skill, and you can actually be good at note-taking. So there's a thing of how do you actually take notes that are efficient so that you don't take too much time in kind of detailing absolutely everything / rewriting the book, but that when you come back even a month or two later, you should be able to understand what you're doing. So I don't know what it was for you, but you can see that for me, I kind of went through a lot of different areas and a lot of different things that I had to learn. And so, in my case, I can easily forget things if I'm not actively doing so.
Yeah, it's exactly the same situation in physics. It's actually I actually still really don't know the answer towards. I mean, there's a scenario when you're looking at a problem and you see something that will illuminate some aspect of it. You've no idea how much emphasis to give that avenue in terms of depth, because there's a couple of different ways you can do it. You can just, like in the context of a coding project, you can maybe Stack Overflow it, see if someone else has done something similar and write it up. But again, you're completely skimping on the understanding in that case. Sometimes it's, and that's not actually always a problem in a computational sense, because there's just so many things that you use, libraries you leverage, even if you have to use Linux and stuff like that, that you've no hope of understanding the entirety of it. It's like sometimes when an error pops up, unless someone has had that error and has had an expert answer before, you're looking into the abyss and you've no clue how to go about fixing it. Like you just don't have the prior knowledge. So to be honest, I still don't know. I still don't have a full answer on gauging the right amount of emphasis to give stuff. Like even with certain research papers. So when you're taking notes and stuff, there'll be some papers I might have spent like an hour and a half detailing, trying to understand exactly how the architecture is working, only to find out that it's totally irrelevant to what I'm doing. So yeah.
I'd say it's a common thing as well. It's like it's an experience thing of knowing what might be important, or at least skimming through it and seeing if it actually is in any way important. And I think in the School of Maths, at least, my supervisor he seemed to know everything basically. So there was like I could ask him about anything, and have to take notes and then research, more stuff. But still, it's, I suppose in the School of Maths you would have your supervisor or even other people that you could ask if you were stuck on a problem, and it's not bad. And it actually would be a good thing. Like if you had someone that you knew, they were also in this field, and maybe you don't want to bother your supervisor too much, or your supervisor doesn't know, you can ask other people. And that expands your network. The more people you talk to, the more people that know you is good. Because everyone seems to know everyone. It's in theoretical physics,
Yeah, it was a little different for this project. This is not at all a slight on Stefano, because obviously he's a complete genius. But with this stuff, he just didn't know. He had no experience on it at all. So and one of the nice things about Stefano is when you ask him a question, he's no clue. He'll just put his hands up. He admits where he's got no remit or no useful perspective to offer. So I did, just because of the difficulty of the architecture. There was a lot that was hidden there. The difficulty of the architecture and problems with its implementation and stuff meant that I had to reach out to a lot of the authors of the library and stuff. So I was kind of leaning into that networking aspect that Chantelle was talking about. I got to talk to some really cool people at MIT and Harvard and EPFL. It's certainly with the coding project. It's probably similar in abstract TP projects as well. But with the coding projects, and because things are on GitHub and projects are being tracked, there's really good version control on stuff. It necessitates that you engage with the experts on it. Which is coding, programming projects are really good at being incremental. So, it's unavoidable that you'll interface with the authors if you want to understand exactly what your issue is and what other issues there have been in implementations and so on and so forth.
Perhaps? Sorry.
Well, this is kind of a new thing. I was wondering if you could give some perspective on picking topics for the final year project in both the schools, and if you have any advice in that regard.
Go ahead.
Well, in my case, a lot of people, number one, if you're looking up professors on their School of Maths webpage, that might not be updated for multiple decades. So if you are interested in, let's say, what a specific person does, even before you get to select or you see what projects are available, the best thing is to actually just look up at some of their recent papers. And that will tell you kind of what it looks like. Is it more differential geometry? Is it more this integrability? Now, you might not understand anything, but that's one thing. But also, a lot of professors, when they actually give you, let's say, when it's released, the projects, they might link a paper or two. So Furloff linked that main paper with his TTbar deformation of the light cone gauge. Now I had some experience. I really liked kind of the module that I took with him. So I was, I had a good vibe, let's say, with this. And I did like the idea of investigation in something like this. And it wasn't, I saw the word string theory, and it sounded cool. But I think most important is at least to weed out things that you definitely know do not spark joy. Because you're going to be at it for the better part of a year. And it's kind of like enthusiasm is an important thing. Enthusiasm in learning and seeing what you can get out of it. That's kind of my advice that I can think of right now.
Sure, yeah. I mean, I had a bit of an issue with picking my project in that I knew beforehand what I wanted to do it on. So I brought, because I've just been interested in this area of symmetry or where neural networks and AI and stuff, I brought the idea to Stefano because I've done some summer internships in the past, and I've worked guess, tangentially with Stefano for a little while, and I know he's a lovely guy, and he's got interest in AI and physics and all that. So I brought it to him, and he thought it was a nice idea, and we were going to run with it, but unfortunately, School of Physics does not allow that. So I couldn't, basically they were putting up a massive fight about like not allowing custom projects and stuff like that. So in the end, it was just luck that I picked it and no one else picked it or ranked it as highly. I have problems with that as like I don't think that that's awfully reasonable to upcoming students to, if you are interested and have picked an area and have someone who's willing to facilitate you researching in that area, that you'd be constrained in that manner or have a project that you bring to them be put up for lottery. I don't particularly like that, but unfortunately it's the state of affairs at the minute. But hopefully that changes in the near future. At the minute, I think the best you can do is just pick your supervisor, like, you know. Yeah, go ahead.
Are the choices competitive when you're like choosing from the list?
Depends. There's some that are more competitive than others, I think.
Perhaps. I think it's pretty hard, at least it's pretty hard for me to say, because I did this project when I was in lockdown, completely isolated. So,
Nice.
so that means I could also, like, in terms of time spending on this, you're like talking, what was, before I ramble, question. The question of, how to pick them. I think perhaps certain also professors might have, like, more people would go for them even just based on how they are. That's one thing. I think I think your year was particularly bad for some reason for people not getting the projects that they wanted.
Yeah, some people had so what you do is usually you rank order them. I think there's other problems regarding the actual algorithm itself, not only the allocation policy, but the algorithm itself, but we won't get into that. And you'd rank order, like, you know, you'd have a big list and you put down your top 6. There's some people that didn't get their top 6. You're like, how in the name of God does that happen? I'm sure they could, like, benefit from one of these, a cheeky, you know, like, cheeky bit of grading to say, because there's no way, you know, that someone missing out on their top 6 choices has minimized any error function whatsoever. But there was quite a bit of that in our year.
Also, I think that you don't actually put your name down for specific projects, but you put your name down, at least in my year, for people to work with. So multiple people might have, I think, might have more than one project. So I actually don't know if that was an option or they could take more than one person at the same time. I wouldn't know about that.
I'm not really too sure on that either. I think, like, if professors have put forward a general gist of a project that they wanted to do. Like, I talked to Professor Tristan McLaughlin before on about a maths idea I had, and he basically said that he couldn't agree to it straight away, but if I got him as a supervisor, then that would be, like, we could just choose from there, even if he had proposed or put forward a different project to selection. So, yeah, I mean, I think basically the supervisor, choosing your supervisor is the best you can hope for at the minute. You know.
And I would say also don't be afraid to, like, ask people if you're kind of interested in a specific area. Actually ask, number one, ask people who have maybe worked with them before, which is really important, because you can't underestimate the importance of the connection, so the compatibility of you and the supervisor, not only in kind of this bachelor's thesis, but even going forward, especially like doctorates. Mm-hmm. And so that's a fair thing, you know, and it can really be hard to be supervised by someone that you just do not connect with, because you're relying on them also for emotional support in this.
A bit, actually, a little bit. I mean, I don't know, you couldn't. I've heard of horror stories where just, not even in STEM, but actually in the arts block, where just certain supervisors are needlessly disparaging towards, like, errors that students make, or not even errors that they make. It's like where it's so subjective, they just get, I don't know, really harsh and stuff, and it doesn't have a great impact on the students. Like, I know even though I haven't seen in STEM a bad example of it, I just know how useful it is to have a nice supervisor. Like it's, I don't know, at the end of the day, even though it's all quantitative, there's humans behind it, like, you know, so. Yeah, Stefano's really nice. I would recommend him. I've also worked with another guy in the past, Professor Lewis Jones. He's a lovely supervisor. Both of these people are really good for just putting you forward in the best way possible for like CV stuff, but also just encouragement and stuff. So those are two that I can definitely recommend. You know.
I would recommend Frolov, and I wouldn't just recommend him because you're recommending the
Yeah.
thing, but I really would like. There's a thing of sometimes understanding how people talk, and that sometimes what may seem like criticism isn't actually. Sometimes you prefer a little bit more, let's say, support or at least validation, but fair enough. You know, it's still like there's a difference. You know,
It's tough love, like.
yeah, it's not even tough. It's just yeah, you can do this and this and this. That's good. Kind of straightforward. So even if maybe someone is afraid, he's actually a really, really nice guy, really kind of solid and straightforward. And if you ask him, he will offer information. That's what I'd say. I've worked with, and I am still working with Manuela Kulaksisi, and she's in a really nice area of like conformal field theory. It's actually quite open in terms of like learning things and even maybe doing some calculations, perhaps even kind of at a bachelor's level. So, and she is also really nice, very supportive, and I would also recommend her. I suppose if you don't really know what exactly you want, because I didn't really have like a specific thing that I wanted to do. I just wanted to do something. So first, you can even just base it on who did you like as a lecturer, and that's kind of valid. Somewhere to go from, at least. That's fair.
Any other questions?
Do you have any other, I know this project is kind of solo journey, but do you have any collaboration with your peers or anything in your student very near year where you can be like, I'm banging my head against the wall, take a look at this thing?
I mean, it's kind of.
Not really exist.
There's a little bit of it. Like it's actually only really happening now because the projects are mature enough that people know what they're doing a bit with them. Like so, in computational stuff, I mean, if someone comes to you with a problem, you can kind of help them debugging it. It's not even that you'd be better fit to understand it. It's just, have you ever heard of like rubber duck debugging, where it's just like you're going through your project, banging your head off your computer, and you just have a little rubber duck there that you explain your problems to. Essentially, like try to figure it out. That's you could just be that person for someone else in a computational project that needs some debugging help. But recently, like I'm starting to find there's another student, Ruth Moriarty, that I honestly just met today and found out what her project is on. It's like different things to do with spatial statistics. So it's like statistics on a sphere. And it's like, oh, well, that kind of fits really well because I'm doing symmetries of a two-sphere or the special orthogonal group in 3 dimensions. So like it fits really well. I think it's just a little bit too narrow a time window to facilitate proper collaborations, but it's very nice to like experience the feeling of just like, you know, going, oh shit, like they're on the same thing, we're on the same plane, and then you know, even though we can't like follow through with the collaboration now, it could be possible for the summer and stuff. And that's just a nice prospect, like.
You can't understate, I suppose, the need just not even a collaboration, but just discussion. I find that right now, because I didn't have anything like that. So during, like, I didn't really talk to anyone about what I was doing. I mean, obviously the presentations are a nice way to kind of see what everyone else is doing. But I think it is true that you can start doing it once you get a little bit more academically mature. So you just gain more knowledge,
you gain more strong knowledge, maybe overall knowledge, maybe niche knowledge, that you can then, like you said, you just talk more in depth and ask more in-depth questions, even if different people are doing maybe different things, if that makes sense. I will also say, I know this may not be like a collaboration thing, but I think it's really important to also attend, if there are, let's say, seminars and things like that. I did want to mention, like the School of Physics has a seminar series, and School of Maths has at least 3 a week. One of them is theory, which goes over my head quite a lot, so that's not important. But there's actually like 2 things, and that kind of gives you an idea of what, like, maybe even PhD students and just more research looks like. So if you're interested, that's a thing when you're doing a research project. Things like attending seminars. Well, at least, you know, I could do that for my thing. I didn't know a lot. That's what I'd say. It was a lot of gibberish, but you're exposing yourself to a lot of stuff. And then you can then collaborate with other people talking about that, I suppose. It's pretty good.
I can't resist the temptation, but if you're interested in improving your presentation skills, TPSA is available 3 times a week, Monday, Tuesday, Wednesday. Just saying.
You guys are very lucky to have this. That's what I'd say. Is there?
Yeah, any other questions? Yeah? Okay, we'll call it at that.